Physics for Life. This is a quick revision video of chapter Alternating Current. Alternating current. It is that current which varies in magnitude continuously and reverses its direction periodically. Its value at any instant is given by I is equals to I naught sine omega t, which is equals to I naught sine 2 pi ft, where this I naught is the peak value of AC or current amplitude, and the frequency of AC supply to our homes is 50 CPS, and the average value of AC over a complete cycle is 0. Next is direct current. It is that current which flows with a constant magnitude in the same fixed direction. Average or mean value of AC. It is that value of direct current which sends the same charge in a circuit in the same time as is sent by the given alternating current in the same circuit in its half time period. So I average will be equals to 2 by pi I naught, which is equals to 0.673 I naught. Now next is effective or RMS or a virtual value of AC. So it is that value of direct current which produces the same heating effect in a given resistor as is produced by the given alternating current when passed for the same time. So its value is 1 upon under root 2 I naught, which is equals to 0.707 I naught. Now next is alternating voltage. So it is that voltage whose magnitude varies continuously and direction reverses periodically with time. Its instantaneous, average and root mean square values are respectively given by E is equals to E naught sin omega t, and E average is equals to 0.637 E naught, and E RMS is equals to 1 upon under root 2 E naught. Now next is phasors and phasor diagrams. So a rotating vector that represents a sinusoidally varying quantity is called a phasor. A diagram that represents alternating current and voltage of the same frequency as rotating vectors, phasors, along with the proper phase angle between them, is called a phasor diagram or Argand diagram. Now next is AC, a circuit containing resistor only. An alternating voltage E is equals to E naught sin omega t applied to a resistor R drives the current I is equals to I naught sin omega t in the resistor. The current is in the phase with applied voltage, and peak value of current I naught is equals to E naught upon R. Now next is AC circuit containing only an inductor. So an alternating voltage E is equals to E naught sin omega t applied to a pure inductor L drives the current I is equals to I naught sin omega t minus pi by 2. In the inductor, the current in the inductor lags behind the voltage in a phase by pi by 2 radian, and this is a peak value I is equals to E naught omega L is equals to E naught XL, peak value of current, and this is the root mean square value of current. I RMS is equals to E RMS upon XL equals to E RMS upon omega L, which is equals to E RMS upon under root 2 omega L. Now next is reactance. So the non-resistive opposition to the flow of AC is called reactance. It may be inductive reactance XL or capacitive reactance XC. Now next is inductive reactance. It is the effective reactance or opposition offered by an inductor to flow of AC through it. It is given as XL is equals to omega L is equals to 2 pi FL, and the SI unit of inductive reactance is ohm, and for AC XL is directly proportional to F, and for a DC F is equals to 0, so XL will be equals to 0. Now AC circuit containing only a capacitor. An alternating voltage E is equals to E naught sin omega t applied to a capacitor C drives a current I is equals to I naught sin omega t plus pi by 2 in the capacitor. The current in the inductor is ahead of the voltage in the phase by pi by 2 radian, and the peak value of current I naught is equals to E naught upon 1 upon omega c, which is equals to E naught upon xc. Now root mean square value of current IRMS is equals to ERMS upon xc, which is equals to ERMS upon 1 by omega c, which is equals to E naught upon under root 2 into 1 upon omega c. Now next is capacitive reactance. So it is the effective reactance or opposition offered by a capacitor to the flow of AC through it, and it is given by this Xc is equals to 1 upon omega c, which is equals to 1 upon 2 pi fc, and the SI unit of capacitive reactance is ohm, and for AC Xc is inversely proportional to its frequency, that is 1 by f, and for a DC f is equal to 0, so Xc will be equals to infinity. Thus a capacitor allows AC to flow through it easily but blocks DC. Now next is impedance. So it is a quantity that measures the opposition of a circuit to the flow of current through it, and so determines the magnitude of the current in a DC circuit. This is the resistance R alone, and in an AC circuit the reactance X also has to be taken into account according to the relation Z square is equals to R square plus X square, where Z is the impedance triangle is a right angle triangle whose base represents resistance R, perpendicular represents reactance X, and hypotenuse represents impedance Z of the circuit. From this triangle, the phase angle phi between the voltage and current is given by tan phi is equals to X by R, and or cos phi is equals to R by Z. Now next is AC through a series LR circuit. The alternating voltage leads to the current by a phase of angle phi. So instantaneous voltage is equals to E naught sin omega t, and expression for instantaneous current is I is equals to I naught sin omega t minus phi. And peak current I naught is equals to E naught upon under root R square plus XL square, which is equals to E naught upon Z. And now impedance Z is equals to under root R square plus XL square is equals to under root R square plus omega square L square. Now phase angle is phi is equals to tan inverse XL upon R, or phi is equals to cos inverse R by Z. Now next is AC through a series CR circuit. The alternating voltage lags behind the voltage by phase angle phi. Instantaneous voltage I is equals to E naught sin omega t, and instantaneous current I is equals to I naught sin omega t plus phi. And here the expression for peak current I naught is equals to E naught upon under root R square plus XC square, which is equals to E naught upon Z. And this is impedance Z is equals to under root R square plus XC square is equals to under root R square plus 1 upon omega square C square. And phase angle phi is equals to tan inverse XC upon R, or phi cos inverse R by Z. Now the series LCR circuit. So for a series LCR circuit connected across a source E is equals to E naught sin omega t, the current I is given by this I is equals to I naught sin omega t minus phi, which is equals to E naught upon Z sin omega t minus phi, and where this Z is the total effective resistance of the LCR circuit and is called its impedance. And Z is given, its formula is given as Z is equals to under root R square plus X L minus XC in the bracket and whole square is equals to under root R square plus in the bracket omega L minus 1 upon omega C whole square. The phase angle between the voltage and current is given by tan phi is equals to XL minus XC upon R, and cos phi is equals to R upon Z. The voltage leads the current if XL is greater than XC, and it lags behind the current if XL is smaller than XC. Now resonance condition of the LCR circuit. XL is equals to XC. The impedance of LCR circuit becomes Z is equals to under root R square plus XL minus XC whole square, which is equals to R. The impedance is minimum and hence the current is maximum. The circuit is purely resistive and the voltage and current are in the same phase. This is the resonance condition of LCR circuit and is satisfied at the resonant frequency given by Fr is equals to 1 upon under root LC into 2 pi. Now next is Q factor. It indicates the sharpness of resonance. It is defined as the ratio of the resonant frequency to the difference in two frequencies taken on both sides of the resonant frequency, such that at end frequency the current amplitude becomes 1 upon under root 2 times the value at resonance frequency. So Q factor is equals to resonant frequency upon bandwidth, which is equals to omega r upon omega 2 minus omega 1, which is equals to omega rl upon r, which is equals to 1 upon r under root L by C. Now next is power in an AC circuit. So the average power in a AC circuit consumed per cycle is given by P average is equals to ERMS IRMS cos phi, which is equals to E naught I naught upon 2 cos phi. Here the cos phi is called the power factor, which is the ratio of true power P average to the apparent power ERMS IRMS. And so the power factor cos phi is equals to R upon Z is equals to R upon under root R square plus in the bracket omega L minus 1 upon omega C whole square. Now first case, for a pure resistive circuit, phi is equals to 0, P average is equals to ERMS IRMS is equals to E square RMS upon R. And second, for a pure inductive circuit, phi is equals to pi by 2, that is 90 degree, and P average will be equals to 0. And for pure capacitive circuit, phi is equals to minus pi by 2, P average will be equals to 0. So now next is wattless current. So the current in an AC circuit is said to be wattless if the average power consumed in the circuit is 0. If the component IRMS sin phi of alternating current in an inductive or capacitive AC circuit, the phase difference between the voltage and current phi is equals to plus minus pi by 2. The power factor cos phi is equals to 0, and so the current is wattless. Now next is energy stored in an inductor. So when the current in an inductor grows from 0 to I naught, the magnetic energy stored in it as this U is equals to 1 upon 2 U naught, this is L is I naught, this is L, and this is I naught square. Now next is energy stored in a capacitor. The energy stored in a capacitor when it is charged from 0 to V volt, U is equals to 1 upon 2 CV square is equals to 1 by 2 QV, which is equals to half Q square C. And next is AC oscillations, LC oscillations. When a charged particle, when a charged capacitor is allowed to discharge through a non-resistive inductor, electrical oscillations are constant amplitude and frequency are produced. So these oscillations are called LC oscillations. The charge of the capacitor satisfy the equation of SHM, that is d square q upon dt square plus 1 upon LCQ, which is equals to 0. So instantaneous charge q is equals to q naught cos omega t, and instantaneous current I is equals to minus dq upon dt, which is equals to omega naught q naught sine omega t. And angular frequency of free oscillations, that is omega naught is equals to 1 upon under root LC. And the frequency of free oscillations f naught is equals to omega naught upon 2 pi is equals to 1 by 2 pi under root LC. The energy in the LC circuit oscillates between the capacitor and the inductor, but the total energy remains constant. Now next is choke coil. So it is an inductor with a large inductance used to reduce the current in an AC circuit without much loss of power. Next is transformer. So it is a device used to convert AC at high voltage into that of low voltage or vice versa. For an ideal transformer, E2 by E1 is equals to I1 upon I2, which is equals to N2 by N1 is equals to K. Here the suffix 1 refers to primary coil and suffix 2 to the secondary coil, and K is called the transformation or turns ratio of transformer. So first, for a step up transformer where K is greater than 1 or N2 is greater than 1, therefore E2 will be greater than E1 and I2 is less than I1. And second, for a step down transformer where K is less than 1 or N2 is less than N1, then E2 will be less than E1 and I2 will be greater than I1. And now the last topic is AC generator. So it is a device to convert mechanical energy into electrical energy of alternating form, and it consists of a coil of wire that rotates the angular velocity omega in the magnetic field B of a permanent magnet. The flux through the coil varies as phi is equals to NBA cos omega t, where n is the number of turns in the coil having the face area A. So at t is equals to 0, the loop is normal to the field. So induced EMF E is equals to NBA omega sine omega t, which is equals to E naught sine omega t, and current I is equals to NBA omega upon R sine omega t, which is equals to I naught sine omega t. Thank you for watching the video.